Today, we're going to tackle one of the most fascinating and, frankly, one of the weirdest ideas in all of science: quantum entanglement.
To get started, let's just do a little thought experiment. I want you to imagine that you can change something about an object you're holding right in your hand.
And at that exact same moment, with zero delay, your action instantly affects another object, even if that object is clear across the galaxy.
Now, this idea seemed so bizarre, so completely against the rules of the universe as he understood them, that Albert Einstein gave it a famous nickname. He called it spooky action at a distance.
And yet, for all its spookiness, experiment after experiment has proven that this is a real feature of our universe. So what is actually going on?
Well, at its core, quantum entanglement is what happens when particles get linked together so deeply that you can't even describe them as separate things anymore. For all intents and purposes, they act like a single, unified system.
And because they're part of this single system, if you measure a property of one particle, you instantly know the corresponding property of the other one. It doesn't matter if they're a millimeter apart or a million light years apart.
Okay, this is where we have to pause and address the single biggest misunderstanding about entanglement. It's really important to get this next part right.
The instantaneous connection does not happen because some kind of signal travels between the particles faster than light. That would break a fundamental rule of physics. The truth is, nothing is sent at all. No message, no signal, nothing.
So if nothing is traveling between them, how does it work? Well, the answer is that the particles were never really independent entities once they became entangled. They are and always were a part of a single shared state.
So let's walk through the actual process. How does this look in a real-world experiment?
It really comes down to three basic steps. First, you get some particles to interact in a way that links their properties. This is what creates the entangled pair. Second, you separate them. You can move them very, very far apart. And third, you measure one of the particles. The instant you do that, the state of the other one is known.
But, and this is the crucial part, here's why you can't use this to send a message. Even though measuring particle A tells you about particle B, the result of your measurement on particle A is completely random. You can't control it. And if you can't control the outcome on your end, you can't encode any kind of information to send to the other end.
And I really want to emphasize this point. This is not just a theoretical idea anymore. The reality of quantum entanglement has been tested over and over again, and it holds up every time.
In fact, it's so well established that the 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experiments that proved beyond any doubt that entanglement is real.
So knowing that this is a real phenomenon isn't just some interesting trivia. It has absolutely profound implications for how we understand reality, and it's unlocking some incredible new technologies.
The reason entanglement feels so strange is simply because it runs completely counter to our everyday experience. Our intuition is built for the large-scale world we can see and touch. The problem isn't the physics, it's that our intuition just isn't equipped for this. You see, our intuition tells us that objects are separate things, that their properties are fixed, and that if you want to cause something to happen, you have to be right there. But quantum reality is different. It's based on probabilities, systems can be fundamentally interconnected, and those connections can be non-local.
And why does this matter? Well, this understanding is the foundation of a technological revolution. We're talking about quantum computers that can solve problems that are impossible for even the biggest supercomputers today. It's giving us unbreakable encryption methods, and it's paving the way for a future quantum internet.
But beyond all the technology, perhaps the biggest implication is what it tells us about the universe itself. It shows us that reality is far more interconnected than we ever could have imagined just by looking around.
So after going through all of that, what's the one central idea you should really hold on to?
When we see these two particles influence each other in an instant, no matter how much empty space is between them, it's not because a message or a signal or anything at all traveled between them. It's because on the most fundamental level of reality, they were never really two separate things to begin with. They are, and they always were, part of a single shared system.